Good afternoon, everybody. My name is Wes Simpson. I'm president of Telecom Product Consulting. Spend a lot of my time doing training on a lot of different technology topics. And today we're going to try to give you an overview of SMPTE ST 2110 in 60 minutes or less. So, hold on to your seats, we're going to have fun. One of the things I think that's really important to understand about ST 2110 is that it didn't come out of a vacuum. It's the product of a long process, many different innovations over a number of years. And I thought I would sort of trace the evolutionary tree a little bit of some of the IP video standards and specifications that we've had over the years. So one of the first ones that came out back before 2000 was called Pro MPEG Coder Practice 3. And essentially what that did was it took MPEG-2 transport stream packets and put them into RTP packets to go out over the public internet. It included a forward error correction scheme, and that evolved into SMPTE 2022-1, which is the forward error correction scheme, and -2, which is the actual way that you take the compressed video and put it into RTP packets. From that, we got TR01, which is a specification from the Video Services Forum and is widely used. Feel free to grab an empty seat here. So that is definitely a viable standard today. There's actually been a recent update to it. And we have JPEG 2000 compressed video over transport stream, again, all over IP networks. Another variant was ST 2022-3 and -4, which took 2022-2 and allowed you to do variable bitrate streams. So most of the work before this was constant bitrate. This was really the first variable bitrate system. So once we start completing the tree for the compressed content, we're starting to think about uncompressed content. And one of the early specifications for uncompressed content was RFC 4175 from the Internet Engineering Task Force. Now this was the first IP transport standard that I know of to take raw pixels, so no compression, no reformatting, just the actual exact pixels from the picture image and send them out over an IP network, again using RTP. Audio did the same thing. With AES 67, we took uncompressed audio samples, so the direct audio that we get from a microphone, sampled 48,000 times a second. Took those audio samples and put those directly into an RTP over IP transport system. So these are both pure media essences being transported, and those were covered in the specification TR03 from the Video Services Forum that talked about how these relate together, timing and things like that. Another mechanism for doing uncompressed video and audio over RTP was something called ASPIN, also known as SMPTE's Recommended Disclosure Document 37. Now that's neither a standard nor a spec, it's simply a documentation of a particular way that video was being put into IP packets. Another very important variation, which I think is going to survive in our market for quite a while, is something called SMPTE 2022-5 and 6. Those take a complete SDI signal, so every bit of a 270 megabit or a 1.485 megabit or a 2.97 gigabit video signal and wrapping that directly into RTP over IP. So these are both very good specifications and standards in the case of the ST 2022 for putting uncompressed video over IP. A slight variation to this to accommodate some timing differences was TR04 that worked along with TR03. So now we're ready for the big stage. We're ready for 2110. 2110 isn't a single standard, it's a family of standards. We have 2110-10, which is the system level specification, sets some overall rules, talks about timing, all that sort of system level type of applications. And we'll go into that in more detail. ST 2110-20 is how you take uncompressed video and put it over an IP network. Very similar in concept, but definitely different in execution from RFC 4175. ST2110-21 is a little bit of a strange being in that it doesn't tell you how to put media bits into a packet. What it tells you is how the packets need to behave on the network. So this is a standard that says we don't want all of our packets to go out in a burst. We want our packets to go out smoothly in a controlled manner so they won't cause problems for our switches, for our receivers, for all the other pieces of hardware in the network. So it's kind of a pacing or a traffic flow thing. And we'll talk about that, of course, in more detail. 2110-30 is uncompressed audio over IP, and it's very, very similar to AES-67. In fact, getting these two different systems to interoperate is a fairly simple process. That, of course, has a very widespread applicability, and again, we're sending our video and our audio using separate standards. ST2110-40 was developed new for the 2110 suite. It also is based on an RFC that was developed at the same time. That's how we take ancillary data, all those extra things that we need to make money with our video. So advertising cues, closed captions, time codes, all kinds of other data that we need that normally is inserted inside an SDI. Well, since the SDI doesn't exist anymore, we needed a way to transport that over IP. Then we have another interesting standard called 2022-7. What that does is it talks about how we can take one stream, send it out over two different networks, and use a receiver that can take both streams and pick only the good packets that come through. So 2022-7 is a very valuable technology, particularly for very high reliability networks over a wide area delivery system. 2022-8, let's not forget that. Basically, that's a way to take one of these 2022-6 signals and synchronize it so that its video is in alignment with an ST2110-20 stream. So again, a very useful, but maybe not mainstream application for video transport. We have 2110-31. That's how we take AES audio, which can be a wide variety of different signals, and transport that over an IP network. Again, sharing the timing and sharing all the other aspects of 2110. Recommended practice 2110-23 is something that isn't released yet. We're expecting it to come out soon. But what 2110-23 does is it provides you a mechanism to take a very large image, divide it into smaller images, and send those out, each one of them as a 2110 stream. And we'll talk about that towards the end of the hour here. And then we have 2110-22, which now we're taking compressed content, but we're putting it into the 2110 domain. So this again hasn't been released, but it's on the way out. This is for constant bit rate, lightly compressed video, where it's primarily used for things like taking a 4K UHD signal, maybe from 12 gigabits down to 2 or 3 or 5 gigabits, so you can fit them inside a 10 gigabit network. So there's a couple different compression schemes that are associated with that. So as you can see, there's a lot going on here. We're going to talk about all the different parts here that start with 2110, and for 2022, there's lots of good reference material out there. So here are the published elements and their formal names for each one of 2110. So system and timing, uncompressed video, video stream packet shaping, uncompressed audio, the AES audio streams, and then the ancillary data. So if you go to the SMPTE website, you can get those today. They're not free, but you can get them. The new elements that are coming out, the first one, actually this is a free document, should be posted any day now, is a roadmap that explains how these different parts of the standard work together. And there we have our constant bitrate compressed video in 2110, and our single video essence transport over multiple ST2110-20 streams. So, just rolls off the tongue, doesn't it, right? Anyhow, so let's take a look at why 2110 is so important. The existing state of the art in about 2012, 2013 was to take SDI signals and encapsulate them over IP. So we took the entire SDI signal. So we took our video, we took our audio that was embedded in the video. We took our data that was also embedded in the SDI video. We took that whole stream and we sent it out as a stream of packets on our network. At the far end, we could depacketize that, we could de-embed those signals, and we could basically have the same exact functionality that we had with an SDI router done over an IP network. Now, of course, this was originally developed for wide area applications. It was designed to go bring signals from sporting events on the West Coast to studios on the East Coast, things like that. But it is conceivable that you might be able to use this in a studio environment. The big drawback to 2022-6 is that I've got to transport very large streams. Every time I want to get a video or an audio or a data stream, I'm dealing with a packet stream that's going to be running on the order of about, well, 1.5 or 1.6 gigabits or 3 gigabits per second if it's a whole SDI. And it's very hard to go in and process just a single part of a stream. The big advantage, of course, is that once I embed all these signals and I keep them together, they're perfectly synchronized. As good as they are here, they'll be at the destination. 2110 takes a different approach. Here we're taking each type of media and sending that out as a separate stream. So what does that do for me? Well, first of all, one of the things it does is it drops my bit rate a little bit. So we'll do a little math exercise later on, but you can see that the SDI video here is actually a narrower bandwidth signal because all we're sending are the pixels. We're not sending all the other overhead, the audio, the ancillary space. It's just the pixel data that actually makes up the picture. The audio signals, those are also set completely separately. So you can have one audio stream in an IP, or inside of an IP packet flow. You can have 16 audios inside of a packet flow. It's your choice. But they are sent separately from the video. And then up at the top here are ancillary data, the important bits, captions and time codes and things like that. Those can also be sent as a separate IP packet stream. Now to tie all these things together, we have something called Session Description Protocol. What SDP does is it gives you all the information you need to find these streams and to process them correctly. So it gives you the media format, so it tells you what kind of image it is. It tells you the size of the image, it tells you the frame rate, it tells you the addresses where you can find these different attributes. So SDP files are very, very important. The other key technology to make all this work is something called Precision Time Protocol, PTP. That gives us a way to very accurately timestamp every single packet coming out from our sender so that our receiver can reconstruct their stream. It can figure out how to align the audio with the video. It can tell which metadata goes with which frame of video. And that timing is distributed throughout the entire system. So every device, every sender, every receiver knows that timing and can actually process the data without having all sorts of overhead. What we've done in this system is we've completely eliminated the need for a sync network. If you're familiar with a lot of SDI video devices today, you have a external sync input, extra little BNC, and that's a whole separate network for blackburst or tri-level, or in audio we use the DARS signal. There's all sorts of sync signals that we distribute today. That's not necessary anymore. All we do is we give every device a very accurate clock, and they can figure out when the next frame of video is going to happen, when the next sample of audio is going to happen, et cetera, et cetera. So, very powerful. And let me just give you one quick graphic that shows you the benefits of having 2110 versus 2022-6. Here we have a network that we've got our audio embedded in our video, we've packetized it, and we have a step in our workflow where we want to process the audio. So when we want to process audio in 2022-6, we have to de-embed, well, first of all, we have to depacketize. So we have to take it out of an IP packet, make it back into an SDI. Then we have to de-embed the SDI signal, and we take the audio out. We have to process it. Then what we need to do is we need to re-embed it. So we need to put that back in to the SDI, then we need to repacketize it and send it along its way. So if I'm an audio processing device here, and I want to handle 2 channels of audio, I might have to have a 1.5 or a 3 gigabit input just to handle, just be able to get access to the audio signals I need to work with. On the other hand, over here using 2110, what I have is, because each stream is individual, I can simply select the audio streams that I need to process for my audio processing device. So if it's 2 streams, I need 3 megabits of interconnect in and out, process that and keep it going. Now, if you're paying attention, you'll notice, you say, hey Wes, how do I keep those things in sync? That again goes back to precision time protocol. The PTP is going to tell us when this packet is created, tell us when this packet is created. When they get to the far end, we'll be able to use those timestamps on those packets to figure out how to realign things, okay? So we don't need to be embedding and de-embedding, but we do need to be resynchronizing and realigning our packets when we go to process them, when we go to send them to viewers, do compression, all those other things. So definitely a step forward, but it adds a little bit of complexity to our network. We've got to get the timing out there. We've got to have intelligent end devices. So let's look at the parts of a video signal. So a full SDI frame is normally going to have some active video, and we're going to process that with ST2110-20. It's going to typically have, many times, embedded audio. So that is normally carried as a series of bits, maybe 16 channels of audio, embedded in the horizontal ancillary space. And then we have our vertical ancillary data space, and that's for all of our other metadata, time code, format description, captions, add triggers, all that good stuff. So each one of these different parts of that full SDI frame has its own standard for how it's going to be transported. So let's talk about 2110, which is the overall standard. This is the system level specification. So it tells us a few things. First of all, what's the maximum size packet that we can have? The maximum standard size is 1460, okay? You can have jumbo datagrams, like we use in some of our file recording systems, things like that today. They can have up to 8,960 bytes in them. So that would handle a 90,000 packet frame. Oh, thank you, thank you. Yeah. We have a, so that's in the 2110-10 standard. 2059-2 is the precision time protocol. That's an IEEE standard, but there has to be a SMPTE profile for that. That tells us how often we send messages, how often we have timeouts. It really brings that home to be totally applicable for video networks. If we're exchanging information between 2110 and AES 67, there's a few constraints. We have to pick some values within these profiles that align up. And let me tell you exactly what that means. A profile is something like, I have to send an announcement message out once every second. I have to send a synchronization message out once every 1/8 of a second. And those numbers are adjustable for different applications. For video, SMPTE has a standard. For audio, AES has a standard. They overlap, so we can pick a set of profiles and parameters that work together between those two environments and make them play nicely. RTP timestamps on every packet. Part of the RTP header, which we'll talk about in just a minute, is a timestamp, and that's tied to a particular value of a clock, again derived from PTP. The interesting thing for video, if we have a frame that needs, let's say, 3,000 packets to transmit it, every single one of those packets will have an identical timestamp. So that when we reassemble that video in the receiver, we just look for all the same timestamps and we know that they all belong in the same frame. So for real-time sources, this should be the image capture time. For SDI converters, when we're converting something from maybe a tape deck or an external feed or something coming into our network, we're going to define a particular point in that SDI, and we're going to use that as the timestamp for that frame once we convert it into 2110. And one other thing that's kind of subtle and maybe a little bit deep for what we're talking about today, but we're not allowed to deviate from the SMPTE master time. With 2110, all media clocks have to have 0 offset, which means that every device will be in frame as long as they conform to the 2059-2 profile. They'll all be identical for all the same types of media. So how do we encapsulate the video? Well, we're going to take multiple things called P groups, and I'll tell you what those are in just a minute. But P groups are groups of pixels, a very obvious name. So we're going to take a bunch of groups of pixels. We're going to apply a header, and this header is going to tell us about the pixels in this particular packet. Then we apply a standard RTP header. The RTP standard has been out for a couple of decades now. It's used for all kinds of media transport. Basically, all those different video formats I showed you on the evolutionary tree all use RTP. User datagram protocol, that's a standard internet protocol. That's been around since the early 1980s. IP, of course. And then we have our Ethernet layer here. So we've taken our pixel groups and we've built up into a full Ethernet data frame that we can send out over basically any Ethernet type of transport system. So now we've got a completely encapsulated signal. So let's talk about a pixel group. So a pixel group is a way to carry data about related pixels, okay? So the P group size depends on the sampling format. If we're running 422 video, we have one type of P group. If we're running 444 video, we have another P group. Fortunately, all of these P groups are listed in the standard. You don't have to guess about it. In 2110-20, all the different types of video that we could think of writing the standard are in there, and we define their P groups exactly how they work together. The reason why we have P groups is that there's 2 rules for every P group. The first rule is that every P group must have an integer number of octets. Well, what does that mean? Well, an integer number of octets means that if you count the number of bits in the P group, it has to be divisible by 8. So I can have a P group with 32 bits. I can have a P group with 40 bits. I can have a P group with 80 bits. What I can't have is a P group with 37 bits or a P group with 26 bits. It's got to be a multiple of 8 bits. And that's so it will fit nicely into a packet. The other rule about a P group is that pixels that share the same samples must be in the same P group. Now, we're not here to have a whole discussion about color science, but a very common format is 422 10-bit. That's what we use for SDI. That's what we use for HD SDI. That's what we use for 3G SDI. So here with 422 10-bit, we're carrying Luma samples, each at 10 bits each, and we're also carrying chroma samples. But we don't take as many chroma samples as we have Luma samples. We undersample. So with 422 10-bit, if we look in the standard, we see that it says a P group is 2 pixels and 5 octets. So it's going to look like this. We're going to have a blue color difference 10-bit sample of 10 bits long. We're going to have one Luma sample of 10 bits. We're going to have a red color difference sample of 10 bits, and then we're going to have another Luma sample of 10 bits. So if you got 10, 10, 10, and 10, that's 40 bits. Just happens to be divisible by 8. So we have 40 bits, 5 octets. We've got a P group. So remember this P group because we're going to use it in a little while. 422 10-bit is 2 pixels and 5 octets. Okay? So here's just a picture of what's in the standard, just so you see it. So a little bit of freebie. Don't tell SMPTE I gave it to you. So. But what we have here is different coloring formats, different, ICTCP. If you're doing 16-bit floating point, your P group will be 8 octets long, and it will have 2 pixels in it. Some P groups have 1 pixels. Some P groups have 8 pixels or 6 pixels in them. So there's a large variety, but they're all listed in the standard. Maybe we'll just call this a little teaser. So here's what a video packet looks like. The top part of this is a standard RTP header. This is straight out of the Internet Engineering Task Force. All RTP packets have a version number, a couple of flags which we can skip over, a C-source count, which is defined to be always 0, so that means you're going to have zeros here and you're not going to have any contribution sources here, which is fine. Then we have the M bit, which I think is my favorite bit out of this whole header. Everybody should have a favorite bit, right? The M bit is a flag that we use to indicate the last packet of a video frame. So if I've got a frame of video that's 3,000 packets long, the very last one of those I'm going to set the M bit to be a 1. And what that means is if you're a receiver, you scan through that incoming packet stream, wait till you see an M bit, and then you know that the next packet is going to be the start of a new frame. The other important thing about the last packet of a frame is sometimes you don't have enough data left to fill up a whole packet. So it might be a little bit of a little dwarf packet, a little stub. And the M bit would just flag it, hey, this packet might be different size than the other ones. The next item here that we have is a payload type. The payload type is used to indicate the exact format of the data that's going to be in this RTP datagram. So for uncompressed video, we use our own self-defined payload types, and that's part of the information that goes in that session description protocol. For audio, we also define our own payload types, although there are some that are standardized. There's a bunch of different values available, anything from 96 to 127. You can set your own value. And as long as the receiver knows what the sender is sending through the exchange of session description protocol, they'll be able to figure out how to decode that signal. The next thing we have is a sequence number. So this is key for RTP. This number goes up for every packet in a particular flow. So it's a 16-bit number, starts at 0, counts up to 65,000, what is it, 536, I think. And then when it gets to the max value, then it wraps around to 0. So that's how we can tell if we're missing packets, if packets are out of order, if something needs to be fixed in the stream, the sequence number is going to tell us about that. The timestamp I just mentioned, for video, the timestamp is the same for every packet in the same video frame. For audio, the timestamps are going to increment, and we'll show you how that works when we get to 2110-30. The last thing in the standard RTP header is a synchronization source identifier. And basically what this does is it tells us the identity of the source used to create the timestamps. If two streams are coming from the same source, you can look at their timestamps and compare them. If they're coming from different sources, you might have to do something a little different when you're working with them. So that's the RTP header. Now for video and video only, we have an RTP payload header that's customized just for video. And let me show you a few key features of that. The first thing it has is an extended sequence number. So it takes this 16-bit number, adds another 16-bit number for a total of 32. The reason we need that is that if we're working with high bit rate video signals, a gigabit, 3 gigabits per second, we're going to be generating 100,000, 200,000 packets per second. Lots and lots of packets. If our packet counter only goes up to 65,000, that's going to be wrapping around several times a second potentially. With a 16-bit number, that wraparound goes out to being a dozen hours, 13 hours, or whatever. So this allows us a lot more time before we have to reset our sequence number back to 0. The next thing is very specific to video. We have the length of sample row data. That tells us how much data is inside this packet, how much data is contained in the P groups. This is listed in bytes. And then where the pixel data inside this image came from, which sample row, and where the offset is. And let me bring up the next slide to explain what those are, okay? So here's our video image, okay? And the first thing we're going to do is we're going to get rid of everything that's not video. We're getting rid of the vertical ancillary space, the horizontal ancillary space, just send the raw pixels. Okay, recurring theme here. The first packet I send for this video frame, I'm going to number it as packet 0. It's going to start at sample row 0, so the first row of pixels in this whole active video array are going to make up packet 0, and it's going to start at position 0, so the offset is 0. So this is the easy one to figure out. Packet 0 is sample row 0, offset 0. Packet 1 might continue that, might be some more pixels from that line. Now in this case, it's still going to be sample row 0, still the first row of pixels, but now we're going to start it at an offset point. This x is equal to the length of this earlier sample in terms of pixels. So let's say if this packet had 500 pixels in it, this offset would be 500, so this would start at the next pixel in the sequence. And remember, we start counting at 0. We might have at the end of a line, we might have a packet that wraps around. In this case, packet 2 wraps around. And so it's going to have 2 pieces of data in it. It's going to have information about this little chunk of pixels, which will still be sample row 0 with an offset of 2x. And then it'll have this group of pixel groups, and this starts at sample row 1, but it has an offset of 0 because it's again at the beginning of the line. So we just keep doing this across. It's like a typewriter. We go to the end of the line, we hit return, we keep going. We just keep making packets, packets, packets all the way down till we completely send every pixel that's in the active video. So that gives us an overall system. Now let me just back up to the previous slide real quick. When we have 2 sets of data in the sample row, we repeat this information twice. So in the terms of packet 0 and packet 1, we only have 1 set of this data. Packet 2 in that example I just showed you, I have this data for the first little fragment, and then I have another set of data to cover the part that starts on sample row 1. Okay? So remember that. Now, let's do a little calculation. And now, why am I doing this? Because I want everybody to get out their calculator and play? No. What I want to do is have you kind of understand how this encapsulation works, okay? So for us to do this, we're going to have a few steps up here, and then I'm going to show you the calculations. You don't have to do them yourself. I've saved you that effort. So we figure out the image size, the number of pixels on each line times the number of lines. The sampling system, we're going to use 422 10-bit because it's very popular. The frame rate, 5994, okay, standard North American. If this was if we were doing this at IBC, the frame rate would be 50, and it would give us a different result because there's less pixels in a 50 hertz signal than in a 59.94 signal. No problem. So now we have to figure out our RTP payload size in bytes and pixels, okay? So our max UDP payload is 1460. We're going to stick with that. Our UDP and RTP header, one's 8 bytes long, one's 12 bytes. So we're going to take away 20 bytes there. And then we're going to have that RTP payload header we had. Now, we're going to use a worst case number. We normally say, well, you only have to have 1 set of pixels in a sample row. This is going to handle the case where we have samples from 2 different rows. So this is conservative. Our number that we calculate here will be off by about 0.2% from the actual true measured speed, but it's going to give us a very good accurate way of measuring things. So that means I've got a payload of 1,426 bytes available once I've taken the 1460 and subtracted everything. Now what I'm going to do is I'm going to calculate the maximum number of P groups and pixels in the packet. And we're going to pick up peppers afterwards. But anyhow. All right, so using this table that we had before, and we all looked at this, I hope you remember, we have 5 bytes in a P group for a 422 10-bit signal. We're going to take our 1426 bytes and divide that by the 5 bytes in each P group, and we're going to get 285.2. But we can't have a partial P group, okay? So we're going to round that number down and say every packet in this stream, we're going to have 285 P groups, okay? Now, who remembers how many pixels are in each P group for this? Remember we showed it, and I told you to remember it. 2, right answer. I'd give you a t-shirt if I had one, sorry. All right, so 285 P groups times 2 pixels per P group means that there's 570 pixels per packet. Okay, so let's leave that up there. Now we have to determine how many packets are in a video frame. So we take our image width by our height, just like we normally would, multiply them together, 2.073 pixels per frame. Divide the pixels, the total pixels by the pixels per packet to get the packets per frame. So we take that 2 million number, divide it by our 570, and we say that we have 3637.89 packets. Now you can't have a partial packet. So this time we're going to round up to see that we have 3,638 packets in the frame. Last step, well, almost last step. Now we have to figure out how big each packet is. So we have 285 P groups, 5 bytes per P group, plus our payload header, our RTP header, our UDP header. We need an IP header, we need some Ethernet stuff, and then we need something called preamble and gap. Basically, that's extra data that we need before and after every Ethernet frame. So our total size of this packet on the wire is 1,528 bytes per packet. Last step. We need to figure out the stream bit rate, packets per frame, times the frame rate of the signal. So we knew we had 3638 packets per frame. We're going to multiply that by 5994. We're going to multiply that by the packets per second. We're going to multiply by the packets, the size of each packet. We're going to multiply that by 8 because we're going to convert from bytes back to bits. And we get our number, 2.65 gigabits per second. So this is actually saving us bandwidth. The standard for a 1080p 60 or P5994 signal is 2.97 gigabits per second. So we've actually put in all these IP headers and saved ourselves some bandwidth because we got rid of all the horizontal, we got rid of all the vertical. All that ancillary space is gone. This is just pure packets, pure video pixels. Timing models. Okay, this is a little tough. If you don't get it, it's not a big deal. But the basic concept is that we can't take all the packets from a frame of video and send it out all in one big burst. That's going to cause all kinds of problems. If I had a camera connected directly to a display, I might be able to get away with that. But if I've got 2 cameras and I burst them both at the same time, what's going to happen? They're going to have all sorts of packets arriving in my switch. There's going to be congestion, and some of those packets are going to get lost. So we don't want to overload our network buffers, and we don't want to overload our network receivers, okay? So we have to allow a little bit of variability, but we don't want to allow a huge amount. So 2110-20 senders need to follow 2 constraints that are specified in our network compatibility model and our virtual receiver. Network compatibility means that we're not going to overflow the buffers in the switches. So we've got about a 10% fudge factor here. We're going to assume that the buffers drain 10% in the video that goes in. So if we're sending a 2.7 gigabit signal, we're going to have to allow about 2.7 plus 10%, so about almost 3 gigabits of space on our IP network to carry that stream intact. The virtual receiver is a little bit different. This is how much buffer I need at my input to make sure that I never have too much data, which means I would overflow and lose packets, and to make sure that I never have too little data, which means I would underflow and my video would be interrupted. So we're going to model these out perfectly. So let's take a look at what happens. All senders must have network compatibility and virtual receiver compatibility. So if you look at how we send packets out, there's 2 ways of doing it. One is linear. If I'm sending out, let's say, 3,000 packets for every frame of video, I could just spread those 3,000 packets out during one frame time. The other thing that I could do, which is actually even a little bit more friendly to the devices on the end, is I could use a gapped model. So if I have a video stream that's let's say an SDI, it's going to have pixels sometimes, but it's also going to have blanking intervals, the vertical blanking interval in particular. With this gapped model, I model that same behavior on my IP packet. So I send IP packets whenever I have pixel data, and whenever I don't have pixel data, I don't send packets. What that does is it makes it very easy for like a switcher or a display or something that's processing videos from multiple sources to always know that I'm going to have pixels at some times and not have pixels at other times from all my inputs, whether they're SDI or 2110 or 2022-6. So the gap model is very friendly. The linear model is actually pretty useful for some compression systems and things like that. And also we use it for different senders. So we also have different sender types. We have narrow sender, which is the one I just described where we have the gap. We have the narrow linear, which is the one where I don't have a gap. And then I have a type W, which is the maximum receiver buffer is much larger. And the reason I have that is because sometimes you're going to be working in a software-driven source, something that's generating graphics or something that's generating maybe animation. You might have something coming from a cloud environment where you can't control your packet flow really specifically. So type W is a much wider specification, but it allows you to work still compatibly across multiple different networks. So with our senders across the top, we have narrow, wide, and asynchronous receivers. So a narrow receiver works with a narrow sender. A wide receiver works with all kinds of other senders, and I'd make a crummy football joke here, but I'm not going to do that, I'm sorry. And then the asynchronous will work with all the different types of senders, even if the clock is not identical. So think about a type A receiver as kind of having a built-in traditional frame store. You can have slippage. You can add or remove frames. It can overflow things along those lines. So these categories, each time you send out a video stream, you have to announce whether it's a type N or a type NL or a type W. These are things that you buy. You buy a synchronous narrow receiver. Synchronous wide receiver is going to have a larger buffer. It's going to have more input delay. And an asynchronous receiver is going to have to be very flexible to handle differences in timings between different networks. All right, enough about video. Let's talk about audio. Audio is much simpler. We don't have a payload header. We take our audio samples, whether they're 16-bit or 24-bit, and we put them directly into an RTP packet, okay? So we only allow 16-bit or 24-bit audio because those are the only ones that have an integer number of bytes, okay? 20 bits isn't going to fly. We're not going to do that in this network. So we're either going to be dealing 16-bit or 24-bit audio. 24 is required behavior for ST2110. All receivers must be able to process 24-bit audio. All senders must be able to send 24-bit audio. We're going to take these audio signals, we're going to group them into an RTP packet, again add our UDP, IP, and then our Ethernet frame, okay? And one thing I did want to mention here, every RTP packet has to have a timestamp. So the timestamp of this RTP header is going to be the sampling instant of the first audio sample here. So whatever the first audio sample is in the packet, that's the RTP timestamp. Now, it's based on AES 67, so 2110-30 is highly identical, okay? There's no offset clock. I already mentioned that a little bit before. It means that all 2110 signals have to be synchronized to the master SMPTE epoch and reference clock. We do support in 2110-30 something called audio channel grouping, and we'll explain that in a minute. And we also have created some receiver classifications to say what the minimum performance requirements are for A, B, and C level receivers of audio, not video. And we also specify that our packet size is going to be 1460 overall, but because we need a RTP header and a UDP header, we have a packet size limit of 1440 bytes. So that means that's how much audio data I can put in one IP packet. No jumbo audio frames, okay? And there's no need, AS67 supports SIP and other stuff, which we don't need. So, P time, packet time. Audio streams are divided into fixed duration packets. So a typical packet duration would be 1 millisecond. So that would be something that we would put in our session description protocol and say every packet in this audio stream is 1 millisecond long. So what does that mean? So if we're dealing with 48 kilohertz sampled audio, okay, that means 48,000 samples per second. 1 millisecond will be 1/1000th of that, or 48 samples of audio in the packet. Simple math, okay? So 48 kilohertz has 48 samples in 1 millisecond. Now each sample could be 2 bytes if it was 16-bit audio, or much more commonly today, it's going to be, each sample is going to be 3 bytes because it's 24-bit audio. So with 48 samples of 3 bytes each, a 1 millisecond packet of audio is going to have 144 bytes of payload, okay? Now that's not terribly efficient. If I'm going to take all that overhead, the IP header and the RTP header and the MAC address and all that stuff, and just send 144 bytes of data, I'm going to have a lot of header and not a lot of data. So what I can do is I can send multiple streams of audio inside one IP packet stream, okay? And in fact, if you look at this number, 144, remember our capacity before was 1440, I could theoretically send 10 different audio channels in a stream. Now in SMPTE, we cut that back and we say that the required behavior is you only need to be able to handle a minimum of 8 channels of audio in one packet stream. But the total audio payload 1440, you could handle 10 if you wanted to, and if your receiver would handle it. So here are the different receiver classifications. These are listed in SMPTE 2110-30. Type A receiver must be able to receive a stream that has 8 channels of audio in it in a 1 millisecond packet, each one of those channels running at 48 kilohertz. So that's, again, that'll all fit nicely into the 1440. An AX receiver, the X means that it handles 96 kilohertz sampling, which a lot of people are starting to use today. Now notice here that we only have 4 instead of 8. Why is that? We have twice as many samples, okay? So 1 millisecond of one channel here is going to take up not 144 bytes, it's going to take up 288 bytes. It's literally twice as much data when we have double the sampling speed. So we have to derate our receiver for that capability. Type B receiver, now we're using a shorter packet time, so we can have 8 channels here, required of audio, but we could have more would fit. Notice down here that the BX receiver with the 96 kilohertz, I can have a full 8 channels here because my packet time is shorter, I have fewer samples. Instead of having 96 samples, I'm going to have 12 samples in there, half of that, 1/8 of my original number. Then the Type C receiver is really cool. Who's ever used MADI around here? You guys have used that. A Type C receiver can handle a full MADI's worth of audio, 64 channels. But again, at 32, at the higher 96 kilohertz sampling rate, I can only handle 32 channels. So those 3 different receiver types are all specified new in SMPTE 2110-30. We also define some extra data that tells you how the channels are grouped within the audio stream. So we can have mono channels, we can have dual mono channels, and I don't know what this is. I think it's mono maybe? I don't know, but anyhow, sorry. We have stereo, we have matrix stereo, left total, right total, for the Dolby fans in the audience. We have 5.1 surround, 7.1 surround, 22.2 surround, way cool. And it's too lazy to list out all the things. They don't even list it in the standard. And then if we don't like any of these groupings, we can say we have a group of 37 undefined channels or 59 undefined channels. We can use any number we want between 1 and 64. With this information, now I could, in one stream, I could send a 5.1 surround, and I could send a standard stereo with that. That would be my 8 channels of audio that would still fit in one stream, but I would use these groupings to keep my stereo separate from my 5.1 surround. Just logically thinking about that. Ancillary data, you knew I was coming to this, right? So the neat thing about ancillary data inside the SDI, it's already packetized. So if you look inside a standard SDI raster, the ancillary data is going to be these little packets, and they're going to look like this. They have an ancillary data flag, a data identifier, secondary data identifier, a data count, the actual data, and then a checksum. So that's what the packet looks like inside the SDI. We're going to take that and we're just going to move it over a 2110-40 packet stream. We're going to take we don't need this flag anymore, but we do need some other information. We're going to need our RTP header. We're going to need a payload header, and I'll show you what that looks like in a minute. And then we're also going to need an ancillary header for this particular information. And this is going to tell us where this particular packet came from in the original SDI, what line number it came from, and what offset it was. Okay? Now, the big thing here is that the line numbers here don't match 2110. These line numbers match the SDI line numbers. So we go from 1 to 1125 instead of going from 0 to 1079. But that's a detail, something to be careful about. Ancillary data payload header, RTP header, exactly what you saw before. The sequence number, exactly what we had for video. Here we have how many ancillary packets are going to be in here, and then a flag. And then it's reserved to bring the total out to 32 bits. So there's our payload header. Now for each packet of ancillary data, we're going to have a C bit that tells us which channel this ancillary packet came from. We're going to have a line number and a horizontal offset. That's going to tell us where it came from in the original SDI. We're going to have a stream number and a flag for the stream. Then we're going to have the original data that was in that ancillary packet, the DID, the SDID, the data count. We're going to have the data. We're going to have the same checksum. So all this information is completely contained in the original ancillary data packet. Then all we have left to do is pad that information out to an even multiple of 32 bits. So that's it. That's how 2110-40 packets are built. Very, very similar to the way they were inside the SDI. For compression, which we're going to be using for 2110-22, we can use visually lossless compression, maybe slice-based instead of compressing a whole frame of video. We do a bunch of lines at a time. There's some popular codecs that are probably going to be the first ones to find for 2022. I'm saying 2110-22. We have VC2 DIRAC that's covered in RFC 8450. And JPEG XS is very much underway. Used to be known as TICO, or very similar to TICO. And that's in the internet draft stage as well. And again, these usually are going to give you a modest amount of compression. It's going to take us down, 2 to 1 to 8 to 1, just so we can fit more signals on a carrier, but visually lossless. Oh, sorry. So 2110-22, constant bitrate compression, must be a registered format. That's why we have RFCs before. Going to have a clock rate of 90 kilohertz, and must be either a NL or a W network compatibility, so we follow 2110. We want all our packet streams to be well behaved. 2110-23 is how we take a single video and send it across multiple 2110 streams. So high resolution streams, high frame rate streams, like ones over 100 frames per second. We've called this multi-port in the past. The cool thing about the way this is being done is that each substream is going to be in and of itself a valid 2110-20 and -21 stream. So we're going to take a large video stream and cut it into 4 perfectly legal video streams. So here's how it looks. The easiest one is a high frame rate situation. So I'm going to take maybe something that's running at 240 frames per second and cut it into 4 streams, each running at 60 frames per second, just by de-interleaving the frames. Another one that's fairly easy to understand is square division. So I take my big image and I cut it into 4 smaller pictures and send each one as a video stream. The last one is kind of the coolest one, but also the hardest one to really understand. Basically, it's called 2-sample interleave. I take 2 pixels from this line and put them in this picture. 2 pixels from the same line, put it in the next picture. 2 pixels from the line below, create a 3rd picture. 2 pixels from that 4th one, create another picture. Now, those 4 pictures together add up when you interlace all the pixels, you get your original image. But the cool thing is that each one of these pictures is going to look an awful lot like this original picture. It's going to look on the screen. It's going to look basically the same because we're just downsampling it. It's going to be lower resolution, but it's going to have, each one of those 4 pictures is going to look the same. So, RTP timestamps, a quick note on that. Video has a 90 kilohertz clock. Audio has a 48 kilohertz clock or a 96 kilohertz clock, okay? So the timestamps for the different media types are not going to be identical, basically at any time other than back at the origin point of the calendar when they were all 0. So, yesterday morning at 11 a.m. Pacific Daylight Time, if I was doing video at exactly that time, my RTP timestamp would have been 625,859,024. If I was taking an audio sample at exactly the same time, it would have been 2,624,000,000, and you can see the rest. If I was running 96 kilohertz audio, it would be 953 million. Now, what's the reason for this? Well, the reason is that the clocks on these systems cycle through. They wrap around or roll over at different points of time. So 90 kilohertz clock wraps around every 13 hours. A 48 kilohertz clock wraps around every 25 hours. And a 96 kilohertz clock wraps around every 12 and a half hours. So every 12 and a half hours, I'm resetting one of my counters. So each one of them is going to have over time, they're going to be adjusted. So what's the impact of that? Well, what that means is that my receiver has to do this arithmetic. It has to figure out how many seconds have happened since my epoch, which was January 1st, 1970. So in this case, I've got a number of days times a number of seconds in a day. I add 37 for an offset because my UTC clock is different than my PTP clock. And I make that calculation. Then I divide it, mod 2 to the 32nd, which is pretty easy with a computer, and that's my result. So each time you make a comparison, if I'm trying to align this video timestamp with that audio timestamp, my devices have to make that calculation. But it's simple arithmetic, it's not rocket scientists. Session description protocol. Isn't fair to talk about SDP. We could spend a whole another class on just SDP. But it's going to give you parameters. It's going to tell you what the video that is inside your signal is going to look like. The image height and lines, the image width in pixels, whether it's a narrow sender, narrow linear, or a wide sender. If you have a different Cmax value, it's going to give you everything you need to know. It's going to tell you the sampling. It's going to tell you the colorimetry. It's going to give you all kinds of information about that signal. For a compressed signal, we're also going to learn things like what the bandwidth is, how, if it's 2110-22, how much bandwidth is going to be occupied by that. We're also going to include the frame rate because we need that for our calculations. And then there's 2 ways of doing it for compressed. For uncompressed video, there's only one way to do it. You have to give the exact frame rate. So 5994 is actually sent as 60,000/1001. That's exactly 5994. So, that's the very basics. We did it in 58 minutes. All right, way to go, team. Okay. I've got time for a question or two, but then after that, we'll turn over to the next speaker. So if there's any questions, I'll grab the mic. Anybody? Yeah, hold on.
Okay. You had an example of the audio being processed.
Yes.
Right? If that happens, does the STP file have to change? Does it?
Okay, so very good question. So the question is if we're taking the example I showed you before where the audio is being processed separately from the video and maybe getting delayed, okay? The answer to your question is yes and no, okay? Some devices are going to update the SDP because let's say it's a big sound mixing board and they're going to originate a whole new audio signal and they're going to bring all that information. They're going to modify that information and they're going to bring it along. Other times you have applications where you want to preserve the original timestamps and you'll configure the device to pass them through, okay? So it's kind of like what we still do in, setting up a regular broadcast network. We have to figure out, do we want to add frames of delay? How do we want to align them to allow for processing? That doesn't go, the need to do that doesn't go away with IP, but the timestamps do make it easier to do that. So sometimes you are going to change the SDP, other times you're just going to let it flow through. Okay? All right, thanks everybody.